a pharmaceutical company,
Mm.
and it was published in the journal. So the overview, basically, new paper, they found a new pocket inside the other pocket, and now there's new compounds that specifically target it, and my voice probably sounds awful right now, so
It did for a
excuse
little
the
bit,
laugh.
yes.
Cool. But
Hey Beth, try something real quick. Can you turn your video off? I want to see if if that affects the share screen, or because sometimes that helps. Do you know what I'm talking about? See if
yeah,
yeah, maybe you won't be able to do it.
okay. I turned
Yeah.
it.
Oh, okay. Yeah. I think continue now, because I think that it just removes some of the bandwidth. You know what I mean?
Yeah. Well, I made
Okay.
my laser pointer blue too.
Oh my God. All right.
Well,
We'll have to talk later about that. Okay.
exciting things. So anyway, this new pocket is called the cryptic pocket because it was previously unknown to the researchers, and it is obviously a new potential drug target because it allows for different and unique structures. It consists of these 3 amino acid residues called histidine 95, which is right here up at the top, tyrosine 96, and glutamine 99, which all are on the surface of KRAS G12C and are able to be kind of translocated. And it is adjacent to cysteine 12 and above switch 2. So this picture right here is actually from the paper that shows how Amgen's compound is bound into this cryptic pocket, and it shifts histidine 95 upwards and outwards. So it allows for this different structure to be able to kind of fill that space. And it's right above switch 2 and right next to cysteine 12. And the interesting thing about this particular pocket is when it forces these 3 amino acid residues out of their original conformation, it also kind of messes with switch 2. So the way I kind of thought about it was like, you can't really see my hands, but like a clam. So if it kind of opens up when you add this new compound in there, so it forces switch 2 down and these 3 amino acid residues upwards. So it allows for different structures. And then this picture over here is just the structure of KRAS G12C that I made in Chimera. So here you have GDP up in the top in its own binding pocket. Here's cysteine 12, and you can kind of tell that there's a covalent bond between their compound and that amino acid. And then these 3 pink structures right here, my laser pointer's not really moving too well, but kind of cover where those 3 amino acid residues are. So that just shows a better picture of the actual structure and how the compound binds into this new area. And so how they targeted the pocket was in the Nature paper published in 2013, compound ARS1620 was used as a tool compound, which essentially means that they found a compound that works and now they can kind of use it as a scaffold to design future drugs. And this compound was not discussed in detail in that original paper. It was kind of published in like the supporting info, but it does have that acrylamide Michael acceptor that was very key in establishing the covalent bond. However, just the rest of the structure itself wasn't really talked about, so that kind of came as a surprise. But during the time that this paper was being published and being accepted into Nature, independent research at Amgen led to the indole-1 compound, which I'll show on the next slide, which occupies this cryptic pocket. So they were kind of working parallel at the same time on different structures, and their backbone kind of led to the discovery of this new pocket caused by the rotation of that histidine 95. So it kind of shoves upwards, and it's obviously a novel binding mode. It means you can design a different backbone to bind in a different way, but still have that covalent bond with cysteine 12. And the key moiety, or like little structure part, is this tetrahydroisoquinoline ring. And that's what it is. It looks like this. And that was the key part that actually shifts that histidine upwards. So they wanted to keep this constant. And then their original compound, this indole-1, actually didn't perform very well in rodent models. So when they injected it in mice, so it wasn't very suitable for like in vivo use, which isn't good because you want to use it as a drug. It needs to be able to function in organisms. However, it provided that good like scaffold, that backbone to identify further compounds and edit different parts of it. So just like in the 2013 paper where they found a backbone that worked after all these 480 tethering compounds, they just kind of messed around with different pieces and parts of the structure in order to make it more suitable for actual pharmaceutical use. So let's see. Come on, change. There it is. Okay, so this is just a figure from the paper where it's comparing ARS 1620 from the 2013 Nature paper compared to their indole 1 compound from Amgen. So here is 1620, and like I said, they kept this part relatively consistent. The only really new addition were these two like kind of altered benzene rings off to the side, but there's that acrylamide that is able to form the covalent bond with cysteine, and this is how it binds into that pocket. As you can see, switch 2 is not disordered, and these 3 amino acids kind of clamp down like a little clamshell. And in the back, it's very faint, but you can see how it forms a hydrogen bond between this nitrogen right here and then the nitrogen in this ring on histidine. So that's what keeps it kind of closed. What that is bad for, however, is that if you have this hydrogen bond, it keeps this kind of shut off. It allows for the cryptic pocket not to be kind of exploited. So what they wanted to do is for this indole lead 1, which is their first compound that they tried that actually opened up this new pocket, is they kept the relatively that same acrylamide backbone right here, but they did a lot of different switching around with some of the interior portions with you have this 4-membered ring and then like a cyclopropane off to the side. But here's that key structure that I was talking about earlier. That's what kind of forces up into this pocket and disrupts the hydrogen bond. So you can see how histidine 95 essentially just rotates upward and outward because of this key structure right here. And it rotates around this like amide bond right there. So that's what they wanted to show, is that because of this differentiation in structure, you're able to exploit a new aspect of the pocket in RAS, and it actually makes it more concentrated, more potent, and I'll explain what like these mean in a second, but lower is better. So once they kind of established this backbone and realized that, okay, we can't really use this in mice models or in people, we need to make it a little bit better, they wanted to see how they could modify the original compound from the Nature paper and kind of make like a hybrid structure between their idea and the original idea from 2013. So they noticed that this nitrogen, N1, in this quinazoline ring, which is these two kind of combined to each other, forms a hydrogen bond with H95. So that's what was showed in the previous slide. And like I said, this is unfavorable because it doesn't access the cryptic pocket because it holds H95 down between that hydrogen bond. So their strategy was just to change that. They wanted to substitute this nitrogen 1 in order to disrupt the hydrogen bonding. So that's what they did over in this figure. So they pursued a range of phthalazine derivatives where the nitrogens are adjacent instead of separated by a carbon. So here they're separated, and here Z and X are nitrogens. And they wanted to see if by changing this kind of backbone within this little tiny part of the structure, they can actually get it to access that pocket. So what it's showing here is in blue is the ARS 1620. So you can see it kind of lays more flat. It doesn't push up and access that new pocket, but they still both form that covalent bond with cysteine 12. And then here is their indole 1 kind of superimposed over it in purple. So I can point out a few key parts that you can kind of see. So here's that cyclopropane that kind of juts out from the end. There's the amide right here with the oxygen and like that 4-membered ring with the nitrogen. And then here is where they switched nitrogen 1. So that's how it originally lays. It lays flat and forms a hydrogen bond upwards to H95. However, when they edit it to form like an amide bond here that can rotate, they allow it to access the new pocket. So what they wanted to do was just change this bottom part of the structure to allow for that rotation to access the new pocket. And then this is actually a huge table of their data for what they did when they were substituting these different groups right here, X, Y, and R. So here is ARS 1620, where X was a carbon just in the benzene ring, Y was the nitrogen, and they didn't have an R group. It just kind of ended. It was just a ring with no attachments. And then here are some of this new data, new terminology. So I'm going to go quickly to just a review of the pathway before I explain things. So if you remember, SOS is a guanine nucleotide exchange factor, which tells RAS to switch out GDP for GTP and turn itself on. RAS does the same thing for BRAF and RAF1, which once again are phosphorylated, turn on, and then continue down the pathway. What's the other thing to point out is that ERK is that final sequence in the pathway, which translocates into the nucleus and then turns on all of these transcription factors and different compounds within the nucleus that allow for cell proliferation and growth. So the key things to remember that SOS turns on RAS, RAS activates RAF, and then the last step in the pathway is this ERK 1 and 2. So going back, this exchange IC50 is an alpha screen assay, very similar to NIA's, and it measures the disruption of the interaction between RAS and RAF. So furthermore, it indicates whether SOS was inhibited. So it tells whether or not GDP was switched to GTP. So in kind of like a better explanation, you want to see a lower amount here because it means the concentration of the compound that is needed to inhibit 50% of the interactions between RAS and RAF. So if you go further back, this just indicates whether or not SOS was able to switch out GDP for GTP. Once this happens, RAS is able to coordinate with RAF. So what you're trying to prove here is that this inhibitor works and it doesn't allow for GTP to switch into the pocket, and B, because of this, it no longer can coordinate with RAF. So you want to see a lower number, meaning that there's less binding. So that baseline number is 0.939 micromolar for their IC50, and then their first compound really just sucked. Like 20.1 is like not good. But their final compound—
Let's be respectful, please.
Okay. But that's like a 50-fold increase, so that's not really good. But down here at the bottom, they finally got it down to 0.101 for micromolar, so that was a lot better. That is like 9 times more potent, so that's what you really want to see. And then this next measurement, this next assay, was a cell-based phospho-ERK1/2 immunoassay, which detects whether or not ERK, that last part in the pathway, was phosphorylated. So this is telling you that even though RAS doesn't coordinate with RAF, does the whole pathway actually get disrupted? So if ERK can still be phosphorylated, that means it can still translocate into the nucleus and do its job and continue this proliferation. What they wanted to prove is that if this compound works, it actually disrupts the rest of the downstream part of the pathway. So once again, you want to see lower numbers because that increases the potency. So their baseline number was 0.831 micromolar, and their final compound, which turns out to be the one that they pursued for the remainder of the paper, got it down to 0.335, which is about 2 times more potent. And then you can see that there's kind of like a wavering within the substitutions on the benzene and whether or not they work. So if you just put a benzene ring, they discovered that that wasn't very helpful. And then as you move down, this ethyl group showed a pretty good drop between like their original substituents, and it got it down to about the baseline except for PERK. And then finally at the bottom, this was actually interesting change. Originally for all their new compounds, the X group, which is this bottom group right here, was a nitrogen, but they switched it to a ketone, so a carbon double bonded to oxygen hanging off the bottom, and they switched Y to a nitrogen from a carbon and attached instead this benzene substituent to a nitrogen instead of a carbon, and that actually proved to be very helpful. So it lowered that p-ERK and the exchange IC50 significantly, meaning that it was more potent and it did its job better at disrupting the rest of the pathway. So this interesting structure right here that they chose with the isopropyl is what they continued to pursue. And then finally, this just shows like a binding comparison between compound 2, which was just a benzene substituent, and then compound 9, which was their most potent and it had that ketone on it. So it shows that you can see how histidine 95 is shifted upwards because of this isopropyl group attached to the benzene. So that's what they were trying to show, is that if you add more bulk to this substituted ring right here, it allows for that disruption of the hydrogen bonding and access to the cryptic pocket. So by just putting a benzene in there with no substitution, it doesn't have kind of enough like force or enough size to access that pocket, but by substituting it more, it forces it upwards and disrupts switch 2 a little bit more. So that's how they just kind of showed to themselves that they can use this backbone and just continue to edit the structures around it in order to make it more available in the cells and function better like in vivo in the mouse models. And that's what I'll get into in the next one, where there's more pharmacokinetic aspects of how these compounds function within the body. So I think that's everything.
Great. All right. It's a nice paper, isn't it?
Yeah, it's really interesting.
Yeah. This is different. I mean, from my perspective, there's sort of been a clear shift from the Showcat paper, which describes, you know, just the fact that this pocket exists and it's targetable, and then they they made a series of compounds and sort of improved them in the biochemical assays that they employed. And then this paper, you can maybe start to feel, and I think next time you'll feel that it's really different, that they start trying to really move and make the molecule into a drug, because they start measuring all these other things that in the Showcat paper they didn't do, because they were really interested in making the tool compound. And then the Amgen people, because they're a pharmaceutical company, they want to make sure that the compound will be successful in animals and then ultimately in people. So it's an interesting transition to see. So you want to keep an eye out for that, I think.